Hello, today we are looking at position to term rule within sequences. Now this is also known as the nth term, and it is a way of describing how you get from the position directly to the term of the sequence without having to go through every step. So let's just have a look at this slightly clearer. Positional language, we are used to using first, second, third, fourth, etc. So in mathematics, obviously first position, first number in the sequence, second position, second number in the sequence, third, fourth, fifth, etc, etc, etc. Okay, now this is a way of being able to skip to the 10th term, to be able to skip to the 202nd term without having to go through every single one of the previous terms. So what we're looking at today is we're going to look at some examples of sequences and how to generate the nth term, and eventually you'll be giving some examples and you'll be generating those nth terms too. Okay, let's start off with a very famous sequence, and I'm going to call this sequence A. 3, 6, 9, 12, 15. Lovely. Now, as always, remember you have commas between numbers, not within numbers. And we're going to start off by looking at our term to term rule. So we're going from 3 to 6, 6 to 9, 9 to 12, 12 and 15. And every time we're adding 3. And hopefully you were all sat there screaming at your laptop going, "We know that, Mrs. Patmore, that's very clear." But we need to move this into the nth term. This is indeed a very famous sequence. It's the 3 times table. And we know that we can do the position multiplied by 3 to get to the term. So 1 times 3 is 3, 5 times 3 is 15. If we were to skip along, we could do 10 times 3 is 30. Note the use of ellipses because you are missing out some numbers. 50 times 3 is 150. 202 times 3 would be 606. But what about n? If it was any number, can we generalise the rule using n as the algebraic variable to show that 3 times anything, any number, is this sequence? Indeed we can. Whole objective really. What we've got here is 3 lots of n, which we write as 3n. And the 3 has come from the fact that we are going up in steps of 3. That's where that 3 comes from. Because we're going up in steps of 3, it means it's 3 times something. And this part here is what we call the first difference. Okay, and you'll get used to the term first difference, eventually second difference, and if you go that far mathematically, third difference, but at the moment we're sticking with first difference. Okay, so that's fairly straightforward. Right, let's have a look at another sequence which is similar but different. 1, 4, 7, 10, 13. Now again, if we look at the first difference, this goes up in 3s. It goes up in steps of 3. Okay, so it's going up in steps of 3. So we can describe this sequence as like the 3 times table because it goes up in steps of 3. Where should I write that? Let's write that over here. Again, I'm just going to use TT for times tables. But this is a huge, huge but. If it was the 3 times table, it would go 3, 6, 9, 12, 15. But it's not. It's going 1, 4, 7, 10, 13. What are we doing to get from the 3 to the 1, from the 6 to the 4, from the 9 to the 7? indeed we are taking away 2. So it's like the 3 times table in the fact it's going up in steps of 3, but we're going to subtract 2. So if I'm writing this out of words, I would say this sequence is like the 3 times table, but subtract 2. So we can use these words to calculate the 10th, 50th, 200 and second term, and then the nth term. So, okay, so if it's like the 3 times table, 10 times 3 is 30, subtract 2 is 28. 3 times 50 is 150, but subtract 2, 148. 202 times 3 is 606, subtract 2, 604. So how do we write this in algebra? Now, like before, the 3 times table we write as 3n, and that's where the 3 has come from, that first difference. And how do we show we're subtracting 2 in algebra? Minus 2. So the nth term for this sequence here is 3n minus 2. Let's do another example. I'm going to call this sequence C. 13, 18, 23, 28, trying to get the spacing right, 33. There we go. First, second, third, fourth, fifth. Slightly out, but there we go. Again, we've got a sequence. It's a linear sequence because it goes up in equal steps. It's an arithmetic progression, AP. So we're going to find the first difference. So we're adding 5. So again, we can say it's like 5 times table. But if it was the 5 times table, it would go 5, 10, 15, 20, 25. What are we doing to that 5 times table to get to 13? What do we do to get from 10 to 18? 15 to 23, 20 to 28, 25 to 33. We're going up. So this time we're adding something. What are we adding? We're adding 8.